we're going to try and actually solve this exact equation, and it looks bad. All right, so trying to integrate with respect to y here, we have y terms. It's a bunch of integration by parts. But there is a nice trick you can do sometimes, and so I'll go ahead and show you that here. So we have this function f of x comma y equals c, and right, so Mars of x comma y plus Neptune of x comma y prime equals 0. So normally what we've done in the past is we went from Mars to f with an integral with respect to x. So we could also go from Neptune to f with an integral with respect to y, but that's going to be really difficult in this case because the n function looks pretty bad to integrate with respect to y. There's an alternative way to do this. So we could take Mars, we could integrate up to f of x comma y, which doesn't look so bad. We can integrate dx. And then that we have that, we can actually differentiate down with whatever result we get with partial y to get back to n and check to see if we're missing anything. So let's go ahead and do that. All right, so let's start with the easier one. So we should have f of x comma y should be the indefinite integral of Mars of x comma y dx, which is equal to indefinite integral of 2xy cubed e to the y. 2xy cubed e to the y dx. That's not a very difficult integral at all here. So the 2x will turn into x squared, and then we have y cubed e to the y. And then, right, we do need this function h of y in case anything's there. Now the next thing is we should have n of x comma y is equal to partial f partial y, and we can compute that fairly easily. So we're going to use the f from here. So we're going to have partial y applied to x squared y cubed e to the y plus h of y. All right, so if we do that, we have, let's see, 3x squared. Well, okay, so this x squared here is kind of like a constant, so I'm going to have x squared. And I've got the y cubed e to the y. That's a product rule. So the y cubed will turn to 3y squared e to the y. Then the other half of the product rule, I need, right, the y cubed will stay the same, and I'll take the derivative of e to the y. And that is just e to the y, so that's not that bad. And then I've got this h of y, so I also need plus h prime of y. I'm not sure what h is, so I'm just going to have to write h prime of y. And I also forgot here, write the parenthesis for the x's. So let me just write that out now. So I have 3x squared y squared e to the y plus x squared y cubed e to the y plus h prime of y. So this was one way to get n, the Neptune of x comma y, but n is also, I can get directly from the ordinary differential equation. So that also has to equal, from the ODE, we have n is equal to 3x squared y squared e to the y. Right, that's the first term. Then I have an e to the y times x squared y cubed. So x squared y cubed, excuse me. And then I have a plus e to the y. And so the first term matches, the second term matches, and I have this h prime of y and e to the y. That's the only thing left I have to match. So I have h prime of y equals e to the y. So then h of y is just e to the y, right? The integral of e to the y is e to the y with respect to y. And so f of x comma y, if I go back to the f I found up here, it's x squared y cubed e to the y plus h of y, which is e to the y. So apparently if we take the derivative of this thing with respect to y, we would end up with the n. And so, right, it's a lot easier to take the derivative than to integrate, right? If we had to integrate Neptune of x comma y with respect to y, that would have been a integration by parts. Looks like there's two of them. It would have been pretty terrible. But with this trick, you can also go in a slightly different direction. You can integrate through one path that's a little easier, and you can differentiate to get back to one, either Mars or Neptune. And then based on that, you can solve for either the h prime of y or the g prime of x to get your matching terms.